the video solutions for problem set 2. So I'm going to go through the coding section of problem set 2, and hopefully you can learn something from my workflow. Okay, let's get started. So we're just going to march through these. Okay, so we have an Excel data sheet titled PCB, and it has the concentrations of polychlorinated biphenyls. And we're going to compare two data sets. So first we have to read this in Python and calculate the mean. So I'm going to open up VS Code and create a new file called PS2, and I'll split it up into cells so I could run this easily. As always, we import our libraries, matplotlib and numpy. Those are the ones we use the most. I like pandas for reading data sets. So first I'll load the data set. So you have to make sure that your data, which is this XLSX file, is in your working directory. That's important. So we're gonna load, whoops. We're gonna load this this Excel file. And it's called, what is it called? Like PCB dataset.xlsx. All right, let's load it and we'll see if it looks healthy. Okay. So yeah, it looks pretty good. Yeah, something you could do is well, it looks like this is the index over here, and it's reading like the double index. So you could fix that. It's a minor thing, but you could fix it by saying index column equals 0. And now when I type data, it should be healthy. Okay, yeah. So I guess the first thing we have to do is part A, we have to calculate the mean. Calculate the mean and standard deviation of the data. So I want to do this for each column. So I'll do it for PCB-A first. Okay. And yeah, this looks like it should work. And I'll say like print the values over here. So it says the mean of the first set is going to be this. I don't know if you guys have seen F strings before, but an F string is kind of a fancy way. Copilot fill this in for me, but like an F string is a fancy way to insert a variable within a string. So the string is mean of PCB, A, colon, etc. They'll insert this value to 2 decimal points. That's what this .2f stands for. So let's just see if it works. Okay, it says, yeah, it seemed to work correctly. So that's the mean and standard deviation of A. And now it's going to do the same thing for B. That's the first part of part A. What else did part A ask for? We got mean, standard deviation. Oh, we need variance. Okay, let me type the variance here too. Say variance of A and variance of B. And I'll add another insert here. Okay. Okay. And yeah, just note that like you should know what the units of these are. The mean is going to be concentration in parts per million. Standard deviation is also going to be in parts per million. And the variance is going to be parts per million squared. It's the concentration squared. Okay. What else do we have to do for part A? We have to find the coefficient of variation and the standard error of the mean for the two data sets. So what even is coefficient of variation? Some of you might have be like, I don't even remember taking notes of this, but thankfully we have Google and we can look things up, and we're independent learners, so that's what we'll do. So the coefficient of variation is looks like the standard deviation over the mean. So you can think of this as like a signal to noise. So the standard deviation is how spread apart your data is, right? That's like your noise, and the mean is the signal. So this is like the noise versus signal. So that seems easy enough to calculate. You just divide one thing by another. So let's do that here. I'll say find the coefficients of variation. And it's filling in these formulas for me. I'll just print them to the screen. Copilot is smart enough to read my mind on these. And I'll just go to 3 decimal points just in case. Okay, Cool. So we have coefficient of variation. This is saying that there's like that the noise is like 8% of the signal, and 5.8% of the signal. Okay. And then finally, we want to find the standard error of the mean. Okay, and it looks like Copilot is already filling a lot of this stuff in for me. It's quite easy. Let's look at the formula. It looks like it's a standard deviation divided by the square root of n. And if you forgot what standard error of the mean is, you could ask ChatGPT about it, or you could just Google it. So it's saying it's the measure of how much discrepancy is in the sample's mean compared with the population mean. So is there like a formula for it? Let me type formula. Yeah, it looks like it's like the standard deviation over the square root of the number of samples. And I guess the intuition here is when as you collect more and more values of n, like more and more samples, you're gonna be more and more confident about what the mean is. If you collect like 3 samples, this is gonna be like a small number here, and you have a large error in your estimate of the mean. But as you collect more and more samples, n is gonna increase. The denominator is gonna increase, which makes the whole error smaller. So you get more and more confident as you collect more and more samples. So it looks like it filled this out for me. Let's test it out. Okay, yeah, I gave a really, really tiny standard error of the mean. So that's 0.009 parts per million. Just tiny. That's like 9 parts per billion. Okay, I think that finishes up part A. So let's just start part B. What is part B asking us to do? It's saying yeah, plot a 100-bin probability-based histogram where the y-axis is probability. Okay, so normally if you try to if I said like plot a histogram of these two things, here's what it would probably do for me. I don't want to do subplots. Um, I'll say like make the histogram. Okay. Let's try this 100. Okay. So just like we're not supposed to just randomly like blindly trust Copilot. We have to think about what this means. So ask us to make a histogram, and it looks like the y-axis here is very large values, like 300 and like 50. That can't be a probability. Probability is constrained to be from 0 to 1, right? From 0% to 100%. So this is not a probability based histogram. So to convert to probability, you have to divide by the total number of samples. So something that's inconvenient about this plt.hist method is that it does the whole process for you. It finds all of these bins. It finds all of these x values. It finds all these bin heights, which are the y values. But we want to like unbundle that process. We want to be able to manipulate the counts, the frequency, and divide it by the total number of samples. So what I would do in this case is I'd ask ChatGPT, how do I deal with this? So um, I'd say like I want these to be probabilities, not counts. So how can I get the bin heights and bin locations? So I can divide by the total number of samples. November. Okay. So let's see what it says. It's recommending this other method called np.histogram. And it seems like this is gonna, it's a method here that's gonna output hist and bins. So hist seems like it'll be the heights of the bins, and bin seems like it's gonna be the location of the bins. So yeah, let's just take this method and let's just see how it looks. So let me just paste this. I'll comment this out and I'll paste this below. Whoa. Okay, let me clean this up a bit. Okay. and we'll see how this looks. Okay. Um, okay, so at least now we're not getting these huge values, but it looks like they're normalizing in a weird way. So it's normalizing by dividing the number of samples and by the bin width. So generally what we're supposed to do is we're supposed to take the histogram heights and we're going to divide it by the length of the data um, to get the um, probabilities. So this looks actually more realistic as a probability. So what it's doing is this MP to histogram is getting the bin widths and the bin heights. Sorry, the bin locations and the histogram heights. And then we're taking those histogram heights, which is the frequencies, and we're dividing it by the length of the data to convert it to probabilities. So now this is like a healthy graph, and we could do the same thing for um for the second data set. So let's just march along and do this, and let's plot a second bar graph with that is corresponds to the next set of data. Okay, that looks pretty good. A couple critiques of this graph is that the font is too small. So let me fix that. Okay, that looks a bit better. Oh, and let me just make the ticks bigger. Okay. And it shouldn't be value, it should be concentration in parts per million. Okay. Now that looks like it's completely correct. Cool. Okay, cool. All right, so that's part B. Let's look at part C. By visually inspecting the two histograms, would you conclude that the two measurements techniques are likely to yield similar or different results? Yeah, they look pretty different. They have different means, they have different standard deviations. Looks like A is more spread out than B. So yeah, it seems like you'll get slightly different results. Okay, so part D, it's saying now plot a density-based histogram where the y-axis is probability density. Um, so there's actually like a nice and easy way to do that for this. So it's actually going to be very similar to what we were suggested earlier. So I'm going to take this, I'm going to uncomment it, and I'm actually going to put another argument here. So you guys probably figure this out by Googling or asking ChatGPT, but if you say density equals true, then you get this, you get like a different y-axis over here. So now it's between 0 and 0.5. And just visually, looking at this, I could tell that this area is probably about 1. Like if this is a triangle, I could find 1/2 times the base times the height. And that looks like 4 times 1/2 times 0.5, which is about 1. So yeah, just from a quick visual inspection, this looks like the integral of or the area under this curve is equal to 1. So that's good. That means that it is probability density. Okay. So let me just plot the rest of this. Now we want to put probability density as the y-axis. And we want to have legend and font size and whatnot. Okay. So this is our probability density. And once again, to reiterate, before, back over here, we had probability. And what this is saying is like if we look at this like blue bin over here, this is saying that there's a 0.03 probability that my concentration for PCBA is in this little bin, which is like from 11.2 to 11.25 or something like that. So it's saying what is the probability of being in this bin? Your probability is about like 3%. So that's what the probability based histogram is telling you. While the probability density, you don't simply read the y values. You have to integrate this distribution to get probabilities. So that's what we've been talking a lot about in class. So hopefully that's familiar to you. I think that's our solution more or less. I think you might want to like make these ticks look a little bit bigger, but I think it looks pretty good. So let's move on. Yeah, we just talked about the difference between probability and probability density. Um, for this one, I'd say like, um, yeah, it's important to have like a mathematical foundation because, yeah, you could visually compare these two distributions and like, yeah, they seem like they're pretty different. But if we had like less than 10,000 samples, it might be hard to know if these two distributions are in fact similar. So yeah, it's important to have like the mathematical foundations just to be able to like say with confidence if two distributions are different. Like yeah, they look different visually, but it'd be nice to be able to say that confidently with math. Okay. Let's move on to part G. Okay, so it looks like they want us to sample two observations from the data set labeled PCBA. And we're for each time we sample these two observations, we're gonna calculate the mean. And it wants us to do that 1,000 times. Okay, and then plot a histogram. So kind of a lot of steps. So it's good to chunk things, break things down. Um, rather than trying to code it all at once, I'm gonna randomly sample two observations a single time. So let's try that out. I'll say part G. Randomly sample twice, or I'll say two samples from PCBA. Okay. Um, okay. So let's see. When I run this cell, and I click or I type sample A, it's giving me two samples. It grabbed sample 9953 and sample number 3850. So it's two random samples, and their values were 10.89 and 9.62. Um, okay. So that looks good. And then if I wanted to find the mean of sample A, then I could use this sample A dot mean. And if I type mean sample A, I have a value. Okay. And now I want to do this 1,000 times. So, like, how do I like loop through this 1,000 times? You're gonna make a for loop. So let me say loop 1,000 times. So I'm saying for I in range 1,000, I'm going to calculate this. And then I want to store these. So generally, if you want to store things, you'd initialize it. So I could say mean samples is an empty list. And every time I calculate every time I randomly sample and calculate the mean, I want to add to this mean samples list. Okay. So let me run that and it finished in no time at all. And if I type mean samples, then I can get all of these values. So it looks like, oh, we want to make sure this random state is not the same. So let's try this again. Okay. Yeah, I noticed that it was the exact same value every time, so that's suspicious, right? It's not actually randomly sampling. So let's check this out again. If I type mean samples, now I'm getting different values each time. And if I histogram the mean samples, uh, then let's see what I get. Okay, yeah, it seems like the histogram is giving estimates that are between like 11 and like, yeah, 9.5 is kind of the extreme, 12.5 is kind of the extreme. And how different is this than before? Yeah, it kind of looks pretty similar to before, right? In terms of the shape. It's a bit more splotchy. Okay, so what do we have to do? Okay, plot a 50 bin histogram showing the distribution of these two sample means. Okay, so let me change the bins to 50. And let me add some labels. And oh, it said it wanted it to be a probability density, right? So you'd say density equals true. And then you'd say probability density. And instead of concentration, I'll say mean concentration. Okay. So yeah, so that, I think that is part G. Yeah, that looks right. Okay. And now it's saying repeat part G by randomly sampling 10 points from the data set and then do the same exact thing. Okay. So I think that's more or less copying and pasting our old code and just changing a single number. We're going to change this to 10. Okay. And then, yeah, it wants us to do it again with 100 points. Okay. So yeah, that looks right. It looks like it's, yeah, it looks like, uh, is it getting skinnier? So over here, this is our first one, right? Um, we have, this is a 2 sample one, and our probability density is, 0 point, like it has a max at 0.65. Over here, it's like 1.75, and oh, it looks like we're getting a little tighter. And over here, it looks like we're getting even tighter. So yeah, it could be deceptive. Like you might just like scroll through and look at part G, part H, and part I, and be like, yeah, they're the same shape. Like I don't see what the difference is. Um, but if you're not attentive, you'd miss that like the probability density is getting stretched, is getting higher, in that this is getting a little bit more constrained. By the time you're sampling 100, you have the mean concentration between 11 to 11.4. Over here, you were like between 10.7 and 11.7, and before you're between like 10 and 12 and a half. So yeah, like it's sometimes it's good to plot these um with the X limits and Y limits set. So here's what I'll do. You could change the X limit and Y limit with this command. I could say X limit is between, I'll say like 9 to 12. And I'll set the Y limit to be, I'll say, yeah, 0 to, let's say 5.2 or something like that. And I'll do this for part G, part H, and part I. So we're going to do it here. Okay, so yeah, this is a better way to see it. Like now that I've set the X limit and the Y limit to be the same every time, now I could compare G, I could compare H, and I could compare I when we sample 2 times, 10 times, and 100 times respectively. And you can see that the distribution is getting skinnier, right? So in this case, it was very spread out. You could say that the standard error of the mean was very large. And then as you increasing n, the standard error of the mean is getting lower and lower. And by the end, as we're sampling 100 times, your estimate of the mean is going to be very precise. It's going to be like very precisely between probably around 11.25 or something like that. So that's what you're supposed to notice. I think a lot of students are probably going to miss this because they didn't set the X limit or Y limit the same and were maybe hasty in making the visual comparison. So yeah, just be very careful with that kind of stuff. Um, so yeah, a couple things I would change about these graphs is I'd make the ticks bigger, and I'd probably give it a label. And I think it would look kind of cool if you plotted all three in the same plot and just gave them like slightly different colors or something like that. But I don't have time for that. So yeah, I think that is the rest of of part one. So we could call it a day. Actually, okay, you don't have to watch this, but I think I'll work through the bonus problem as well. And actually, I'll just ask ChatGPT to solve it, and we'll see how well it does. I know a lot of you guys don't have GPT-4, but it's kind of a really cool tool to help you as you problem solve. I use it every day, like probably like an hour or 2 hours every day. Um, and yeah, let's just see how well it does in problem three. So I'll just like paste this into ChatGPT, and I'll say like, uh, let me just give it in chunks. Okay. So I'll give it this first chunk, and let's see how well it performs. So yeah, we went over this solution in class, so this birthday problem. And we calculated these factorials and came up with an analytical solution. But there's an alternative way to solve this. Instead of using a instead of analytically figuring out these probabilities, we could instead simulate 10,000 classrooms using a Monte Carlo simulation. That means basically we imagine 10,000 classrooms by like using a random number generator. So Monte Carlo is like a casino, and it's like in a casino you roll dice, you play probabilities. So that's why they call it a Monte Carlo simulation. So let's see like how it did this. So it says that uh oh yeah, it looks like this is the analytical solution. There's like a 98% chance that there is a shared birthday. So there's a very, very high chance that there is a shared birthday. Okay. Um, so that's the analytical solution. And then let's see how it did the Monte Carlo solution. So it simulated a classroom. It created a function using this def term. And the function is called simulate classroom. It's taking number of people as an argument. And it's creating a set of birthdays. It wants to see like how many unique birthdays are there. So as you sample, like basically for each person, it's picking a random uh integer between 1 and 365. And if the birthday is within that number, then it returns true. That means it found a shared birthday. And if it doesn't, then it returns false. So this is how you simulate a classroom with this function. And it's saying I'm gonna do this 1,000 times. And when it simulated that 1,000 times in this for loop over here, you see that uh you see like how many times is a birthday shared. So this is kind of, if you follow this kind of protocol or something similar, where you have a for loop and you randomly give each person a birthday, then that's kind of the solution for this kind of problem. So with that, yeah, please like email me or like yeah, go to office hours if you have questions on any of this stuff. Hopefully that's helpful. I hope like you could skip around and like find something useful in my workflow. And other than that, please like and subscribe so I could be YouTube famous. And yeah, have a good day. Take care.